let's recall what we did so far. So we have defined what is meant by a measure space. In other words, if you have a set XA, then what is a meaning of calligraphic A, which denotes the sigma-algebra, and how I can define a measure mu on it actually. So F for calligraphic A doesn't matter. Like I said, one symbol can be used. So we know essentially what this object is and what are the key properties of this object is. Okay, and I gave you an exercise. And we basically proved a theorem about which kind of states all properties of the basic properties of probability measures. But then I gave you an exercise that you can prove the same thing for generalized measure actually. Okay. Fatah asked a very good question. He said that, okay, if we have a measure space, how can I specify this measure actually? In other words, you have some space that in which you can measure up things. The question is how to measure it actually. Okay. The answer is that you can construct the measures. Okay. So the construction of measure would be maybe the topic for last part of the next. We'll start constructing actually. So now what do you call a topic? So maybe in next week in lecture we'll spend on the last part. Will spend on the construction actually, or we'll begin construction of measures from there, from the next lecture. But what I would like to emphasize this and an upcoming lecture is that how can I integrate things with respect to measures actually. So imagine you have a measure space and you have some way to measure the measurable sets actually. Then how can I integrate with respect to measures? So this is what the key intention is, and so I would like to essentially generalize what do you call the previous thing, which is the notion of the Riemann integral actually. So let's get back to the Riemann integral. We discussed in the first lecture that if you want to compute the integral, okay, of a curve under Riemannian sense, okay, and what you have to do, you have to partition the interval and then compute the lower and upper Riemann sums, and then there's Riemanns and infimums, gives you kind of lower and upper Riemann integrals, and then you check the equality that whether they are equal or not, and then you say that okay, the function is integrable actually. So it's not a pretty much classical sense, everyone knows it actually. The Lebesgue version of what do you call integral is basically to see the same problem but from a different perspective actually. So instead of partitioning what do you call the domain of the function, let's partition what we call the image set actually into the subintervals actually. Okay, and what we want to do, how can I integrate things using the partition of why we want to do, there are lots of advantages of it. Okay, one of the key advantages that okay, there are functions which this definition, like in the Riemannian sense, you can't integrate it, but you will see that if you try to integrate them in this sense, you can make sense of them basically, you can integrate it. So what you have to do essentially the partition, okay, and partition the image set, or maybe what do you call codomain, okay, and then take the subintervals actually. So if you take a particular subinterval, so in this subinterval I can take a value, okay, which is going to represent one of the image, okay, on this curve actually, okay. So essentially we can take this as any yk, but it's better to take it as infimum of the values in this actually, okay. If you do this, then I can, so it's like this is the image of what do you call, this is a part of the image set actually. The question is what are the pre-images actually. So in order to see the pre-images, what you have to do, you have to see the points, okay, the key points that lie in this interval, and you know, so this would be essentially the pre-image set. So it's like this is the f inverse of, if this function is f, then you know this interval is f inverse of you know jk, in other words the pre-image set actually. Okay, when you want to compute the area, what you can do that from each such intervals, take yks, okay, and multiply them with the measures of the pre-images and take the sum, and then essentially you're going to get almost the same thing that we have here actually, okay, but with the more convenience. And we see that like this way of argumentation works very well actually, and you know it's a pretty nice way to you know compute the integrals actually. Okay. Obviously here the key question that arises is that, okay, so how do we know? So mu only works on the elements of the sigma algebra. How do we know that this is basically the element of sigma algebras? Okay. So you know obviously we have to assume that these are the elements of the sigma algebra, but we will investigate some properties of f. We will define some special kind of functions. Or you can, so let me rephrase the same question. So for what class of functions this way of integration is valid actually? Okay. Is it the same as the Riemannian, or is some bigger class actually? So we'll say that you know it's a bigger class of function that you can integrate in this way. So obviously it's a huge advantage actually. Okay. Obviously you want this to be measurable, and for the measurability of such a set, this pre-images set, you need some extra structure on the f, and I'm going to define this sooner actually. Okay. So I discussed this earlier. So let's begin by integrating some of the very simple entities actually. Okay. So consider the indicator function. So let A is a subset of x, or maybe omega, whatever you know set you have, and then the indicator function of A is a map from x into the discrete set 0, 1 actually. Okay, and it tells you that you know the indicator function when operated onto some x is going to tell you that whether this set x is in the set A or not actually. So you're going to say that, okay, the value of the indicator function operated onto x is going to be 1 if this x is from the set A. Okay, so it's going to indicate the element is in the set A, and you know, and then what? And
0 if x is
zero
not in A.
if x is not in A actually, or maybe it belongs to the x minus A. Okay. So x minus A. So this is going to be the indicator function. Now, using indicator functions, I can define a simple function. So let's think about integrating, okay, with respect to, for example, abstract measure mu. So x could be any space. So it could be any measure space actually. So I would like to first of all integrate in this abstract space a very simple kind of a functions. Okay, an approach is going to be this one, and let's define something. They are not only simple, but they are called simple functions actually. Okay. So what's a simple function? Okay. Imagine you have a finite number of sets, subsets of x. So these are the finite number of subsets of x. Okay. Such that they are mutually disjoint. So AI intersection AJ is empty whenever I doesn't agrees with J. And so they are partitioning essentially x actually. So the union of I equal to 1 to n, AI is equal to the whole x. Okay, so imagine you have this kind of set here. Now I'm defining a function s from x into what? Into r, maybe something, okay, such that f of x is equal to some real number si, okay, if x belongs to A, okay, for all I, where si is a real number.
We have to assign.
I'm sorry?
We have to assign it.
We have to assign some value. So in other words, essentially what I'm saying that, okay, imagine you have, some chunk of intervals like A1, A2, A3, AN, and on each interval the function takes a fixed value. Okay, so maybe this, and maybe this. So on each sub-interval it takes some fixed value. Okay, so in other words, s of x is s1, fixed s1 for all x from the A1, and s of x is s2 for all x from A2.
Greatest integer function.
Yes. And obviously what I need to do, I have to define another thing. Okay. Well, by the way, I can relax this condition. I can say that, okay, you have, so let's keep it, at the moment, let's relax this condition. Imagine that you have some subsets of x which are disjoint, and you are defining a function on those sets. And I can say that this is equal to 0, okay, if x is outside the union of all these atoms. Okay. 1 to n A. Okay, so if x is outside, then s of x is what?
None of A is contained.
Yes. So therefore you're going to have the map S from whole x of R. I can do something similar, but okay, this one is more general actually. Okay. Then if you think about it, I can write this thing as this actually. So can I say that f of x is basically sum of I equal to 1 to n si multiplied by indicator function of ai operated onto x. Okay? It's precisely the same thing. Think about it. So this x is going to be where? It's going to be in some of the AIs actually. So imagine if it is in A1, okay, then indicator function of A1 of x is going to give you 1. And you're going to get S1 as this result, and rest are going to be 0. Rest are going to be 0. And similarly, if x is in A2, so the indicator function of A2 of x is going to give you 1. It is going to give you S2 and rest are 0. So it's a clever way of putting the same thing actually. It's a clever way of putting up the same thing. Okay? Are you getting the point?
Yes, sir.
Yes. Now I would like to do what? I would like to define, the integral, okay? Integral what? Of such a simple function over whole x, but with respect to the measure mu. Okay? Now keep in view this picture in your head and give me a suggestion that what should be the definition of this cell. So it's going to be obviously summation. I equal to 1 to n, nothing is strange. But what would be the definition? What should I write next?
Times measure of that number. SI times
Point of case.
SI times measure of what? Measure of what? SI times,
measure of AI.
okay, so you're going to have SI times the measure of the inverse image of this guy, or the set where it belongs actually. Okay? But you know, so I might assume that from where it belongs, so essentially what you have to do, you have to do the SI multiplied by, you know, inverse image of SI, inverse image of what? S inverse of SI. Okay? But what is S inverse of SI? So it's AI.
Yes, sir. Completely.
Okay. So it makes sense. I equal to 1 to n SI and the measure of what do you call AI. Okay. Pretty. Okay, we can show it pictorially. Here is the thing. Imagine, okay, so I can take x to be particularly r. At the moment x is abstract, actually it could be anything, but we can always go into r. So I'm saying that, think about it. So I have, so this is my a1, and this is my a2, and this is my, for example, a3. So the simple function says that on the whole interval, the value of the function is fixed actually. So it's a kind of a step function. And here you also have the value of the function and similarly something like that. Okay? And this value is what? So this is S1.
And this is S2.
Okay, this is S2.
And that is
And
S3.
I can put something like this, and this is my S3 actually. And I'm saying that, okay, I want to measure the area, so what I need to do? Okay? So I need to partition the way we do, okay? And I say that take this part and see how much part of, what do you call, essentially, function lies in this interval actually, how much of the images, so it has just one image actually, okay? So if I, for example, compute what is the S inverse of S1? So it's going to be essentially this set actually. And S inverse of S2
Yes,
is going to be this set, and so on and so forth. So it meets with our expectation actually. Okay. So this must be, okay, our result. Are you getting the point? Good. Now,
Sir, S6 is by linear approximation of the function.
it's okay. You can treat it as a linear. So it's obviously not a linear but a constant function.
Yes, sir.
Okay.
Sir,
It's like even elementary than linear. Huh?
what happened when AIs are connected?
Then, I mean, if they are connected, then you have to split them in such a way that they become disjoint actually. Okay, so essentially, this thing works at the moment for this joint thing actually. Are you getting the point? Okay.
Now suitable measure.
So it's like, in other words, if you have any simple function defined on any measure space, you want to compute the integral of it. So here's a recipe to compute it. So let me give you, does this answer our question? Think about it. Now if you take the simple function, if you take the simple function, what simple function? Say for example the same function that kind of made our life miserable, okay, in Riemann integration, same one.
Sum of
F of x equal to x, okay, so 1 if x is in Q, and 0 if x is not in Q, intersection for example 0, 1,
0.
intersection 0, 1.
Sir, simple in sense discern में simple तो लगे बाकी
Simple means that, okay, which is defined on different parts, but it's defined in this way. So this is nothing. I mean, if you see this is nothing, this is just indicate a function of Q.
Yes, sir.
Okay? And now I want to define over whole R, or maybe the interval 0 to 1, which is my domain, this indicate a function of Q. With respect to our measure, okay, I'm vaguely writing the length measure, okay, the length measure. okay, which I'm going to denote by m actually. Okay. Then what does this definition is telling me that how can I compute it? So it's going to be
Sum of
0 multiplied by the measure of the set on which this function is taking value 0. So it's q complement intersection 0 to 1, okay, plus
one
1
measure of
times measure of q intersection
0 to 1.
0 to 1, okay, this actually. Okay, so we got our result. So it's like this guy goes away and you get what this is equal to
simple measure.
q intersection of 0 to 1. Now the question is, what is the measure of this? Okay, so if we treat, for example, roughly, so very intuitively, if we treat length as our measure, then what would be the length of this interval?
One minus
So
0.
it must be 0. It must be, it's a discrete set. So each point has a measure 0. Okay, so it's like each rational number individually has a measure 0 as a set, length 0. So their sum is going to be 0 as well. So essentially, this integral is 0. Don't worry about it, we're going to define this rigorously, but essentially I'm saying that if you treat m as, you know, a kind of a length, then the integral of this is 0. So we are able to compute it, you know, something that we were not able to compute through the Riemann integration. Okay? Alright.
Complement of rational number and complement of whole means q intersection 0 to 1.
Okay, so it would be something similar.
Same level.
So those numbers which are not rational and are in 0 to 1. So I think it's
Sir,
fine.
measurement
Zero
वो नाम बताया तो measurement of the real is infinity.
Q and Q complement कर सकते हैं
वो सर real में rational नहीं था rational नहीं था वो real जैसे कि pin point के तो एक तरह difference होगा उनकी measurement जरूर नहीं थी
We will, when we will define it rigorously, you're going to see. R is a huge line actually. So its length must be infinity apparently. Okay, as per our intuitive notion of length actually. Okay, while Q is a part of it. So if something has huge length, it can have a part of it which has a 0 length actually. Maybe some length which is smaller than infinity. So I think it's not a strange result. It's pretty intuitive actually. Anyway. Alright. So I'm there, I'm here. So let's talk about some of the properties of the integrals of the simple function. Okay. So there are lots of exercises here. You have to do all those exercises, especially in this book, Probability for Finance. So they are by default exercises for you. Okay. Now, question: does this new definition of integrals of simple functions with respect to the measure mu, okay, agrees with the basic properties of the integral that we know, about Riemann integral, for example? So I'm writing property. This is exercise, so you have just mentioning it. You have to prove it for yourself. Okay. Is that, imagine you have two simple functions. So if R and S are simple functions, okay, and they are abstract simple functions on abstract measure spaces, okay, then R and S are two simple functions, then the integral, okay, of the sum, or maybe the linear combination of, these two simple functions with respect to the measure mu must be equal to what? As per expectation, a times, so pull out the constant, times omega, or maybe whatever x that we have, we are taking as our measure space, r d mu, okay, and plus
B times
b times s and d mu. Okay, so just d mu is a symbol actually. So d mu represents, okay, how you want to measure, in this space, the chunk of things, okay,
Yes.
and the part of things actually that you want to do. Okay, are you getting the point? So it's an exercise. Obviously, if r is a simple function, so it must be some linear combination of indicator function. S is a simple function, so it must be as well a linear combination of simple functions. Then, so I can write this whole expression as a linear combination of simple functions, and then the integral of this by definition is going to be something like similar. So it's a pretty
Nice exercise.
easy exercise, a nice exercise to do actually. There's another exercise. That you have to do it for yourself. That if you have a simple function r, which is defined on a measure space, which is less than or equal to s, another simple function s. Okay, then both are what they are. So it's like this comparison is pointwise actually. Okay, so if one simple function in some sense less than or equal to another simple function s, then what relation you can expect between the integrals? So it must be less than or equal.
Same.
So you should have something like this actually. Okay, so this is another exercise for you guys. So you have lots of exercises to do in measure theory. Okay. Now let's play a little bit more with this integral of simple function. Okay. I would like to prove a quick proposition. Okay, which tells another interesting thing, and that this proposition is that imagine I have a simple function which is non-negative. Okay, be simple, so it's a simple function, and then the product of f, okay, with the indicator function of some b, set b, okay, is also non-negative for b in the measure space, okay, so whatever measure space symbol that we are using, okay. And if this is the case, then using this random variable, I can define a new measure which is going to be kind of an induced measure, okay, on the same space. So let me define a measure new, okay, from the same calligraphic a into 0 to plus infinity, okay, such that whenever new is operated onto some b, okay, onto some b, then you have to do what? So this is equal to the integral, okay, of s multiplied by its indicator function over the x axis. Then this guy,
इसके बाद मेजर भी होगा ना सब कुछ
sorry?
इसके पास मेजर भी होगा कुछ
Yes, obviously, there must be the mu actually. Okay, the mu. So essentially what you are saying, that the integrals defined by the simple functions is a measure itself actually. So you can construct a new measure, through integral. Okay.
सर उस measure को हम दोबारा से use कर सकते हैं simple function के लिए.
No, I mean this measure is going to play an interesting role actually afterwards. Okay.
सही.
So in other words, you can say that this is an induced measure, okay, by the definition of integral actually. So it's a measure. It's a measure. measure on A. That's a measure on A. How can I prove it's a measure? Okay, let's do some interesting things. So the first thing is, first of